In this video, I'm going to illustrate carrying out time series regression in SPSS using the Cochrane Orcutt procedure and the Prais Winsten method. So generally you're going to pick one of these. I generally prefer the Prais Winsten method, but I'll show you both of them. The data that we have is collected really over the last year or so. What I did was I took data from Gallup on presidential approval shortly after the presidential inauguration back in 2017. And so these are the values, weekly values on approval and disapproval. So we also have, so basically this variable right here, time, is essentially in increments of weeks. So essentially this is week 1 following the inauguration, week 2, week 3, and so forth. And so I thought it would be interesting to look at various possible predictors of presidential approval since the inauguration. So I've included number of tweets. Our president likes to use Twitter a lot, and so I thought, well, I'll just count up the number of tweets each week and then look to see if that is a predictor of presidential approval levels. Also, I thought, well, we'll look at also the functioning of the economy. You know, as it changes over time, do we also observe variations in approval? So I have actually three different economic indices: the Dow Jones Industrial Average, weekly values, foreign exchange rate with the euro, and the S&P 500. And these three variables were so highly correlated that in the models that I'm going to illustrate, we're just going to use the Dow. Okay, so first off, when it comes to running time series analysis, you want to kind of look to see if there's any kind of trending on your variables. So what I am going to do is just take a quick look to see if there's any kind of trends over time with respect to presidential approval, number of tweets, and the Dow Jones. So you can get a visual on that by going to Analyze, and under Forecasting, you'll notice it's got little sequence charts here. So if you click on that, we'll move our time variable over to the time axis, and then we'll also add number of tweets, approval, and the Dow. And so I'm also going to ask for one chart per variable. So when I click on this, you'll notice that here we've got presidential approval, and it looks like in general it's following the kind of the trend that oftentimes happens, which is immediately after the inauguration there tends to be a little bit of a honeymoon period, and then you start seeing decreases in approval. And it actually looks like there may even be a little bit of a bowl shape here, reflecting sort of a quadratic trend. When we scroll down, we'll look at the Dow Jones, and so you can see in general it looks like the Dow is increasing, maybe a bit of a bowl in here as well. So that's those two. And then the number of tweets, you can see right here also kind of evidence of a quadratic trend in the data. So you can see that, kind of immediately following the inauguration, there wasn't really a lot of trending, but then you kind of see as the year progressed, there was in general kind of a marked increase, and then gradually some decreases. And this probably also kind of reflects, the end of the year, the holidays, and so forth. So it's not terribly surprising. Because basically the data was collected through about January 6th of 2018. So what I'm going to do is I'm going to model, I'm going to start with a least squares regression analysis and discuss that. And the thing about it is that least squares, when it comes to time series data, oftentimes it's not really appropriate. In terms of the regression coefficients, they don't, they tend to, they're pretty much unbiased, but when it comes to the standard errors, because of the time series nature of the data, it generally creates correlated errors, which violates a central tenet of least squares regression. And that violation then can deflate the standard errors and increase the likelihood of making type 1 error when it comes to making inferences about the regression coefficients. Um, so, so let's take a quick look at we'll run the analysis using least squares. And we'll start off, we only have a time variable right here, which is we can model approval as a function, a linear function of time. But as we saw, it looks like there might be some maybe a quadratic trend in the data, and so we might want to investigate that. If we wanted to kind of get a little bit clearer picture or a little bit more information, we could just as easily go into regression, go down to curve estimation, and we can put time on the independent as the independent variable and approval on the dependent, and we can ask for several trends right here to kind of investigate further. Are there any kind of nonlinear trends in the data? And you can see the R-square values for the linear, quadratic, and cubic trends, and you can see that there's a difference here in the R-squares between the linear and quadratic. It looks like that if we were to model a quadratic trend, we'd be accounting for basically over a little bit over 9% additional variation. So, and that trend is statistically significant. So at any rate, I think we're going to stick with modeling a quadratic trend, where basically approval is in part a function of, or where approval is related to time, both in terms of the linear component and also the quadratic component. So to do this, first of all, we've got time, and what we're going to do is we're going to create a new variable called, I'm just going to call it time squared. And so in this case, I'm just going to click time, and then I'll just say asterisk. Actually, if you just use asterisk asterisk there, and then a 2, that is basically telling SPSS to square the original time variable. So the name is arbitrary, but we have to get this right. So I'm going to click on OK, and so now when you look at the data set, we now have a variable called time squared. So now we're going to run the least squares regression. So we'll go to Analyze Regression Linear, and I'm going to put approve in the dependent box and time in the independent box. I can also, if I want to do this kind of incrementally in steps, I can do time squared, and then I can also include my 2 main predictors of number of tweets and the Dow. Under statistics, I'll go ahead and ask for R-squared value and, R-squared change, and then also the Durbin Watson. And the Durbin Watson is utilized to help evaluate whether or not we violate that assumption concerning the errors in the model. And so this is one way in which we can do this. There are other ways as well that are probably a little bit more modern, if you will, but we'll just kind of stick with this for right now. I'm going to click on continue and then on OK, and so now you can see, looking at our general model, we've got the R-square values for each of those models, the R-square change, so basically the change from model 1 to model 2 by adding in that the quadratic trend. We're basically we're accounting for a little bit over 10% additional variation, and then from model 2 to model 3 we're not really adding any additional variation. So there you go. In terms of the regression coefficients, just looking at them, you can see that the relationship between time and approval ratings was negative, and there's the time square variable right here, and so we'll look a little bit more at that later. But then there's not really much going on with respect to the number of tweets and the Dow. But like I said, we have probably a situation where we have correlated errors, and so really, technically speaking, using the least squares regression is not your best bet. But to evaluate whether or not we have correlated errors, we can look at the Durbin Watson statistic, and you can see that we have a value of 1.421. And basically what you're going to do is you'll go into the Durbin Watson tables, and these are the Durbin Watson tables from Tabachnik and Fidel's textbook. This is in the appendix, and they sort of they give you a little bit of information about the tests and so forth and what's going on. And really what we're doing is we're going to enter these tables. The K is referring to the number of predictors, and this particular test essentially, when it comes to testing for autocorrelation, these kinds of tests, essentially you kind of have to think about it as, kind of the mid range, if you will, is 2. So, a value of 2 is basically sort of consistent with a lack of autocorrelation. And then basically as we sort of trend down towards 0, then, we're getting, more and more autocorrelation. And so you can see right here we've got sort of the DLDU, and so basically there's a, the way this test functions is that these are essentially kind of like critical values, if you will. And so essentially you have an interval that is created, and so you've got sort of the DLDU. And when it comes to testing for positive autocorrelation, which is, most of the time that's what you're going to end up with when you're dealing with time series kinds of data like this. And so basically what you have is a sort of a significance test, if you will. And so sort of a significant Durbin Watson would indicate that you have a significant positive autocorrelation. So basically, if your Durbin Watson from your regression kind of falls in this region right here, then you're going to reject the null and basically infer that there is significant autocorrelation. If your value falls, up here, then basically you're going to maintain the null and conclude that there's no significant positive autocorrelation. And then if you fall sort of in this bounds right here, then the test really becomes inconclusive. Okay, so at any rate, what we're going to do is we are going to, I think our Durbin Watson from our regression was 1.421. We had 4 predictors in the model, and we had 50 observation periods. So we are going to kind of, this is the column that we're going to mainly focus in on, and we're just going to keep scrolling down until we get down to 50 or thereabouts. So down here you can see at 50, you can see that we have a lower bound of 1.206 and an upper bound of 1.537, and our value actually falls within that bound. So that actually creates a little bit of a problem, because we're going to infer that basically our test is inconclusive. So we can still do a little bit more in the way of studying or examining whether there's a problem with autocorrelation by if we go to analyze, just rerun the analysis. And I'm just going to do away with all the other stuff and just run one analysis with time square, and number of tweets, and Dow, and then we got approval right here. And what I'm going to do is I'm going to click on save and save the unstandardized residuals, because really what we're doing is we're testing whether or not we have autocorrelation in our residuals. So now I'll click on continue and then on OK. And now in my data set I have a new variable reflecting residuals. And so the idea is that if the residuals are autocorrelated, what that means is that the values are correlated with themselves across time. So for instance, theoretically I could create a lag variable for the residuals, at a lag of t minus 1, which is one time period from the current time period. So to do this, basically I would just I would just highlight, highlight everything in this row, and I can copy and paste this. This is just to illustrate. The computation is a little bit different, but this is sort of the lag. So you can see that the idea is that the residual at let's say time 2 is in part a function of the residual at time 1, because these values are the same. Or the residual at time 3 is in part of a function of the residuals at time 2. And so theoretically, I could even create lags offset in subsequent periods. The way that I can get the autocorrelations, I can get what's called an autocorrelation function and then study the residuals to see if there's, maybe any kind of problem with it. Like I said, I would not be surprised if there was, and so that would make essentially least squares regression not really the way to go, and that's where the Durbin Watson or where the Cochrane Orcutt or the Prais Winsten method come into play. So to study the autocorrelations, I'm going to go down to forecasting autocorrelations. And so in this case, I'm just going to highlight the unstandardized residuals, click on OK, and so now what we see is we get the autocorrelations. So these are the correlations between the current time point and the lags of those time points. So this is a lag of 1 time point, a lag of 2 time points, lag of 3 time points. So if you can imagine, we just created one lag variable reflecting this first lag. And then theoretically, we could create additional lag variables and correlate them. And so that's what these autocorrelations are. And essentially, you can see that we have a positive autocorrelation at lag 1, and then you have a few negative autocorrelations, and then really kind of pretty much middling autocorrelations. So this is called the autocorrelation plot, or excuse me, a plot of the autocorrelation function. And so each bar is essentially, giving you sort of a visual representation of this right here. And so you can see that it looks like we have a lag, a correlation between lag of 1 and the current time point. It looks like there are other possible lags as well. And so, basically these bars reflect 95% confidence intervals, and so the basic idea is that the bar is kind of touching or extending beyond these lines right here. Then that would suggest that that you have a significant autocorrelation at a particular lag. If we scroll down a little bit further, you can see that we have partial autocorrelations. And with the partial autocorrelations, these are the correlations between each lag variable and the current time point with respect to the residuals, but controlling for the previous time points. So in this case right here, you can see, and so lag 1 autocorrelation for the partial autocorrelation will be the same as the first lag 1, but the second partial autocorrelation is going to control for the first lag variable, and so forth. So looking at the this plot right here, you can see that that basically, and this is a plot of the partial autocorrelation function. You can see that really that it looks like there may be some autocorrelation. Really, this wasn't significant at lag 1, but at lag 2 there may be some significance. So it looks like there's probably a little bit of some autocorrelation in the data. So it certainly suggests then that we have to consider that when we are running our time series regressions. So given that, we are going to utilize these two procedures I was just telling you about, the Cochrane Orcutt and the Prais Winsten. And so generally you're going to pick one. And essentially, like I said, I tend to favor the Prais Winsten. You actually end up losing data when you're running the Cochrane Orcutt, so your sample size actually gets smaller. Whereas when you're running the Prais Winsten, you don't lose your observations or lose any observations. But nevertheless, the way that you will run the regression, what you have to do is you basically have to go back here. If you go into File, New, and click on Syntax, then a page will open, and basically I just kind of hit enter, and I'm just going to type in AREG, and that's basically for auto regression. And basically the Cochrane Orcutt and the Prais Winsten methods are used, pretty much assuming an AR1 error structure, or basically an auto-regressive error structure where you basically have the autocorrelation between the current time point and a lag of one time point. And a lot of times this will be sufficient when you're running a time series regression. So now I'm going to type in the names of the variables as they appear in my data set. So I'm going to type in approve, and then that's my dependent variable, and then I'm going to type in width, and the width is essentially saying, well, what are you predicting approval with? So we're using width, and then we're going to type in the predictors. So we're going to type in num tweets. Oops. We have DAO. We've got time and time squared. These are the actual names in the data set. And if you don't have the right names, it's not going to work. Next, I'm going to press backslash and method, and then equals. And then you notice that you've got CO, ML, and W. So you've got Cochrane Orcutt as CO, maximum likelihood is ML, and then Prais Winsten is the PW. So we're just going to start off with the Cochrane Orcutt right here. Also, these methods are iterative. So, if it's the case where you want to raise the number of iterations or change the number of default iterations, you can do that by typing in backslash MXITER, and then equals, and then whatever the maximum number you wish it to be. A lot of times it's not going to reach that number of iterations, but if you needed them, you could certainly get them. So I'm just going to type in 200 just to be arbitrary. So now I will highlight all of this, press the green button, and so now you can see I've got my my information. So you can see iteration 1 is essentially the previous least squares regression. So you can see there's the R-square value, the Durbin Watson, which was exactly what we had previously. You'll notice that we've got ANOVA results, and then down here the regression coefficients, the standard errors, everything is exactly the same as what we ran previously. Scrolling down, you'll see we have iteration history, and so these are essentially cycles through the solution, and then essentially essentially once things sort of stabilize, the cycling stops basically. So here it basically iterated through about 3 times, and so then you've got your final iteration right here. The estimated autocorrelation for the AR1 process was 0.27. The model fit summary, you see the R-square right here is 0.496, and then the Durbin Watson is 1.747. And essentially, when you look at the table, it now looks like it would not be significant. So there's not significant positive autocorrelation, which is pretty much what you would expect. When you look at the regression coefficients, we'll notice that time has a negative relationship to approval levels. So basically, as approval levels as time progressed, approval levels were decreasing. Interestingly, the time square variable was not statistically significant. So it was actually kind of suggesting that maybe the quadratic trend doesn't really fit the data. But keep in mind, you're also controlling for the number of tweets and DAO, and then also the these two variables actually were pretty collinear. So it's not a terrible surprise that this didn't emerge as significant. So looking at the number of tweets in the DAO, you see that both of these predictors were not statistically significant. So at any rate, any kind of hypotheses about the relationship between economic functioning and the number of tweets and presidential approval just sort of goes out the window, at least according to this data right here. Now let's say that we want to go a little bit further, and let's look at running the Prais Winsten method. So in this case, we're just going to change this to PW and highlight and run. And so it also utilizes an iterative estimation process. So at iteration 1, again, this is the least squares regression, and then it's cycled through 2 iterations, and as a result of the final iteration, these are the results here. The Durbin Watson, again, if you consult the Durbin Watson table, it appears that there's no more problem with positive autocorrelated errors. There's the ANOVA table of regression coefficients, and so in this case you see that both time and time squared emerge as significant. So there's, in this case, there's actually some evidence that perhaps you have that quadratic trend. But again, the number of tweets and the Dow were not significant predictors in the model. So so the long and short of it is that it looks like, again, number of tweets and the Dow were not significant predictors of presidential approval across the 50 weeks. Just kind of note too that if you didn't want to incorporate the time component directly, what you could do is something that's called detrending. So we could detrend, say, the number of tweets and the Dow, and then include those in a regression analysis. And detrending just basically means you identify the trend over time associated with, say, the number of tweets and the Dow, and you essentially carry out a regression analysis with your trend variables, which might be time and time squared, as predictors, and each of these variables as dependent variables, and then saving the residuals from those regressions. So essentially you're removing the time component from the variation of those variables, and then you can include those detrended variables in the regression analysis. So you would do that for your predictors, and you could do that for your dependent variable in the model. And basically what happened, I've already done this before, and essentially with this data, and unsurprisingly, the detrended predictors were not significant predictors of the detrended dependent variable, and the R-squared was like 0.004 or something along those lines. It was extremely small. But if you wanted to take time time out of the entire equation and not factor that in, you can see the R-square value is extremely high right here, but using the detrended versions of the variables, the R-square would be very, very low, and that's because the trend component is explaining really most, if not all, of the variation in approval levels. So at any rate, that's just a quick overview of these two procedures in SPSS. Like I said, I would tend to probably favor the Prais Winsten method, just because you do lose some data when you are running the Cochrane Orcutt, and particularly if you have a smaller sample size, then you don't want to lose data and have your power decrease because of that. So at any rate, that's the overview, and hope you find this helpful.